Hi apes, today we're taking a look at Unit 6, Part 4, Nuclear Power, which is our final form of non-renewable energy. I do like to keep this separate from fossil fuels though, because this is a very different type of non-renewable, that it doesn't come from the decomposition of plant or algae material, so this comes from a mineral from our crust. So I wanted to start off with just a comparison of nuclear power around the world, because most of what we use nuclear power for is electricity. And so this is the share of electricity in different countries in the amount of terawatt hours produced, and then the amount of overall, what piece of the pie does nuclear power play when you talk about all the energy sources in a country. So if you take a look here at the United States, it does look like we're a leader in nuclear power because we create so much energy with nuclear power. But what I want you to remember is that United States is one of the top energy consumers in the world because of our developed nation, because we are so highly populated, so we do need a lot of electricity. And so that is a little bit misleading when you take a look at how much energy we create with nuclear power, and yet we're not even in the top 10 as far as nuclear share of electricity. So our nuclear power accounts for less than 10% of our overall energy creation. So when you want to look at maybe a leader in nuclear power, I would focus on France, which doesn't look like it creates as much as we do, but 75% of their electricity does come from nuclear power. So it's just taking a look at the different comparisons of countries and how important nuclear power is in their electricity makeup. So some of the basics, there are two different types of nuclear reactions that we'll refer to: fission and fusion. Now what we use for nuclear power is we use fission. That is our fuel source, or our method. So fission is splitting of an atom, and fusion is combining two atoms. So I'll go over these two processes. So to start with fission, the splitting of an atom, here is our fuel source. Our most common fuel source in the United States is uranium-235. So we hit that uranium atom with a neutron. And so when the neutron is absorbed into this, it creates a very unstable isotope, uranium-236. So that means one neutron was added to its nucleus. So this is incredibly unstable. It's only here for a split second, and then it does split apart into two daughter materials, and then in that process releases a tremendous amount of heat. And this is what we're going after with these nuclear reactions, is we're trying to find an efficient way to get to this heat. Now we call this a chain reaction because not only are these daughter products released, but free neutrons are released as well. So what happens then is this neutron is going to go hit another uranium-235, and continue on with this reaction. So that's why we call it a chain reaction, because as long as there's uranium atoms to absorb that neutron, this reaction will continue to go. Now fusion is the combining of two atoms, and this is the type of energy that our sun consists of. So here we have two hydrogen atoms, and to force those together creates an enormous amount of heat. And then the product here is helium. So for this, we don't have the technology currently to use a fusion reaction to make electricity. We just can't control it. We can't force these two hydrogen atoms together. We do see this type of technology in bombs, but you need a fission reaction to supply the energy to force those two hydrogen atoms together to make fusion. So currently this is under research to find ways to make fusion happen, but currently we don't have the method to use fusion for electricity, so we do fission. Now some other basics is that it is non-renewable because this is from a mineral. So we are not going to be able to make new uranium. So we do consider it to be a non-renewable resource. At some point we will run out of it. Now there are several different types of fuels that we can use, fissionable fuels, but the most common that we have is uranium. Now, uranium is a relatively common element in our Earth's crust, but most of it, 99.3%, is uranium-238. Now you might remember from your chemistry classes that different elements have isotopes. So in an isotope it has the same atomic number but a different atomic mass. So what this means is there is a different amount of neutrons in its nucleus. And so here uranium-235 has 3 fewer neutrons than uranium-238. Uranium-238 is very stable and will not go through fission, but uranium-235 will. And so you will find this uranium-235 isotope similarly to uranium-238. And what we have to do is once we get a sample of uranium, we take advantage of that slight weight difference and we can enrich our uranium samples to be about 4% of this fissionable material. So if you were to have a sample of uranium, most of it is going to be the stable 238, but you might have a little bit of the 235 in there. And so in order to make a fissionable fuel source, we will concentrate the uranium-235 to make it about 4%. So about 4% of that sample would be the fissionable U-235, and that's the sample that we would use for fission. Now with nuclear power, one of the key things with those isotopes is many of them are considered to be radioisotopes. And what this means is as they decay, as they go through a half-life, they give off radiation. So down here at the bottom is an example of half-life. A half-life, you might remember from chemistry and biology, is the time that it takes to decay by 1/2. So it is a time measurement. So here we might have 100 atoms of a nuclear power, or of a nuclear fuel. And after one half-life, you would be down to 50. After second half-life, 25, and then 12.5 and 6.25. So you keep cutting that amount by half. And so you can take a look at this as amount of radiation. You can take a look at this as weight of a product, because they will create daughter products. But every half-life you cut the amount by 1/2. Now, as it's going through this half-life, a radioisotope will give off radiation in the form of alpha, beta, or gamma rays. Now, an alpha ray is going to be able to be blocked by paper. Okay, so it will hit paper and be blocked. It's not very penetrating. It can't move very far, but it can cause damage if you breathe it in, say, to your lungs. Now, beta particles are light. They can travel far, but they would be blocked by something like wood. And then gamma radiation is then the one we're most concerned about. Gamma radiation can travel through both paper and wood and would be blocked by something like lead or concrete. So gamma radiation is the most penetrating type of radiation that we're concerned about. Now, when we make nuclear power, let's go through the parts. So what I want to take a look at is what's going on here in this main general building. Okay, so we'll focus on this reactor vessel right here. So this is the core of a nuclear power. So within the core, you have multiple items. You have coolant, because remember, we're trying to make heat. You have fuel assemblies, which are concentrations of your fuel source. And you have control rods that will help to pace that reaction from going. It can slow it down and speed it up. So you'll have a fuel rod that has the uranium pellets in it. So these pins will have these pellets that have that 4% or more concentration of the uranium-235. And you put these fuel rods together into a fuel assembly. So these fuel assemblies are found in the core of your reactor. Now, these fuel rod assemblies are put into the coolant to help to moderate and slow that reactant down. And the control rods can go in and out of these fuel rod assemblies to absorb neutrons. That's what those control rods do. They can control the pace of those neutrons. So if you want to slow your reaction down, you put your control rods in. They'll absorb the neutrons and the reaction will stop. If you want a lot of reactions to be going on, you pull the control rods out and then neutrons can start flying everywhere. So if you take a look here, you can see that here is my fuel source. Here's my coolant that's in between them. And once this chain reaction starts, a neutron is free to hit other uranium-235 atoms. And so if you want to slow this reaction down, you would put control rods in this gap here, and that would slow the reaction down because they would absorb the neutrons rather than them being able to hit the next uranium-235 atom. So here is our reaction going on. Here is our control rod, or here's our fuel source. And here you have the fission reactions that are going on. So if we pump water in here, then the fission reaction will occur. It will heat this water to steam, and that steam actually gets put through here to turn water flowing in here to steam. So this might seem unusual that I have two conversions to steam. But this red line here denotes that that is radioactive steam because that has come in contact with our radioactive material. So this loop here is radioactive. And so this is our first heating loop to be able to create heat to make steam. This steam is used to turn a turbine. That turbine is connected to a generator, and then the generator is connected to make that electricity. So this should remind you of our steps of making electricity from coal, that we're trying to find a way to heat water, to make steam, to turn a turbine, to connect it to a generator. And so here our fuel, our way of making heat, is that nuclear fission. So here we have one radioactive steam loop, and then here this steam loop is clean. Okay, because all the radioactive material stays within our containment structure. So this is a concrete building that is very thick to make sure that if there's any type of problem, that any radiation stays contained within that building. So the radiation is all contained in here. The steam leaves the building to turn the turbine that is not radioactive. The generator is not in contact with radioactivity. So one of the key things is we have to keep this reaction cool. We have to constantly have a cooling system. So this clean steam loop, the way that we condense this steam to water is by pumping cool water in. So we have a source, we have a nuclear power plant very near to us, and that's Lake Anna. So if you can picture Lake Anna was built for the power plant. We pump cool water in from Lake Anna. It comes in contact with this steam. It absorbs the heat. And if you remember with Lake Anna, we have warm water that comes out. And this is our key problem with nuclear power, is that it creates thermal pollution. Thermal pollution is just warm water. So that changes the quality of water. So it absorbs the heat from the steam, it discharges warm water, but when it transfers that heat, it condenses this water, comes back in to become steam again. And same thing goes here. We have water that's pumping through here, a heat transfer. So we create steam, it comes in contact here, it condenses, comes back here to be heated again. So these are closed loops. The only open loop is right here where we pump cool water in and pump warm water out. Now this is one way of taking a look at nuclear power. And here's another one. It's going to be very similar, except you might notice that now there's only one loop of steam. So this reduces our conversion, so it conserves energy in that way because we have less steps along the way to lose energy. But this is a little bit more dangerous because now everything is coming in contact with radioactive material. So here we have this water loop where we're pumping water in. It's coming in contact with the nuclear heat. So now it is radioactive. So this is radioactive steam that's coming up, coming down to our turbine. That makes the turbine radioactive. And then we pump water in from Lake Anna, condenses that water, and it loops again. So this is a closed loop, so that water is not going into Lake Anna. The water that gets pumped out, the thermal pollution, is not radioactive, it's just warm. Okay, so this again is our only form of direct pollution from nuclear power, is that thermal pollution. But it's the same process that we're trying to find a way to make heat, to make steam, to turn a turbine connected to a generator, and then we condense that heat again. So this is just another method. We have both types of plants in the United States. This one is a little bit more dangerous in terms of radioactive potential. So the benefits of nuclear power is that its direct use does not add CO2, NOx, or SOx, or particulate matter at all from the use. So that's a key thing here, is that it's the use of that power. Because when you have to mine and transport and build these factories, that does create these fossil fuels, that does use these fossil fuels. So the fuel cycle does have pollution, but the actual use of these plants doesn't. Now another thing is, because we get such tremendous power from a very small size pellet of fuel, there's a lot of less land disruption from the mining, because you get a lot more bang for your buck with uranium than you do with coal, oil, or natural gas. So those are some real benefits of nuclear power. But there are some problems, which is why it's only about 10% of our fuel source here in the United States. Like we said, it has thermal pollution. So this is the discharge of warm water. So that does change the water body that it's going into. Transporting the materials is risky because of the radioactivity. And they are very, very expensive to construct, and so that makes the power source as well a little bit more expensive because of all the safety measures that we put into play. So most of our plants are run incredibly safely, and there's a lot of oversight that goes into it, and the cost of the construction to make sure they stay safe is very, very expensive. And then there's a lot of worry about where to put these. A lot of people are afraid of being near a nuclear power plant, and one of the biggest fears they have is the risk of radiation. Now, the thing about radiation is that we are constantly exposed to background radiation. It's actually everywhere around us. But the reason why we are concerned about it is because high doses do lead to cancer. So this is why you don't go get an X-ray for every time you stub your toe, because we do need to limit our exposure to radiation. Now, a properly run nuclear power plant is actually incredibly safe, and there is minimal risk of being exposed to radiation. You're actually exposed to more radiation with a coal plant because that coal is out in the open. So some of our background radiation, it comes from radon gas in the ground, from building materials, from cosmic rays. So we get radiation all around us. It is possible to have a nuclear accident that releases radiation, but it is pretty rare. Now, when it does happen, radiation can biomagnify. So if you remember that it increases in concentration as you move up the food chain. Now, the reason why we're so concerned about our radiation is because it takes thousands of years for it to become safe. Because this radiation decays by its half-life, it takes thousands, if not more, years for it to become a safe material. And this is actually the biggest problem that we have, is the waste that we create is radioactive. And currently we have no method of dealing with that radioactive waste. So currently, this is what we do down here. We store it in a pool, typically on site or very near the site of that nuclear power plant. So deep in this pool, these are all the fuel assemblies of a nuclear power plant. These are used fuel assemblies that are no longer able to be used. Now, the reason why we keep it in a pool is because it keeps it cool, and that layer of water absorbs any types of radiation. So these people are safe up here because the radiation will be contained in this water. So our biggest problem is the waste. We currently have no method of dealing with our waste. There have been options of doing something like long-term storage. There was talk about doing putting a geologic storage in Nevada and Yucca Mountain, and that has since been shut down. So if you take a look at this map, we can see that most of our nuclear power plants are all on the East Coast. Very few on the West Coast. So this was a concern that if we are trying to deliver all of our nuclear waste to Nevada, how do we get it across there? Because this is dangerous material now once it's been used. So this was a real concern. So nuclear power is definitely an East Coast thing. And one concern about this nuclear power is these plants do have a lifespan. They don't last forever because what we're concerned about is safety. We don't want any small cracks to leak out any radiation. And so most of our plants are starting to get to their full lifespan. Typically, a plant operates about 40 years. So you can see all these blue ones that are in that 30 to 39 range. Now, you can get extensions if you've shown that you've updated your safety, but most of our plants are older, and there's not a lot of new plants that are getting renewed or scheduled to be built. So that's our biggest concern, is the waste. But there are also accidents that have happened, and I'll post an article about these 3 accidents. These are our 3 biggest well-known accidents of nuclear power: 3 Mile Island, Chernobyl, and the tsunami that hit Japan that caused a nuclear accident. So it is good to know about these 3 types, and I'll put an article in our Google Classroom for you guys to read so that you guys can understand the details of those 3 accidents. But with nuclear power in the United States, I don't see an immediate future for it until we start to get approvals for new plants to be built. And currently, most of our plants are on the outside.